Hey everybody, we are embarking on a new journey today in section 3. We're talking about multivariable linear systems, so this could be 3 or more variables. And we're going to just jump right in, okay? We're going to learn a couple of different pieces of vocabulary. We're going to learn something called row echelon form. And what row echelon form, I'm going to zoom in here, it's a system that has a stair-step pattern with leading coefficients. And if you're thinking, what on earth could a system that has a stair-step pattern looks like? If you look down here to example number 1, this is an example of row echelon form. Okay, this is row echelon form where you see that the top equation has 3 variables in it, the second equation has 2 variables in it, and the last equation has 1 variable in it. All right, let's talk about Gaussian elimination. And you're probably thinking, whoa, Mrs. Alzarullo, what is happening? Here is what a Gaussian elimination is. Remember how we learned elimination last section? Gaussian elimination is the process. So just like elimination is a process, so is Gaussian elimination of converting a system into an equivalent row echelon form by using one or more row operations. So basically, we're taking something that doesn't look like row echelon form and turning it into that stair-step pattern by using one or more row operations. And so I'll tell you what those are in just a little bit. So what's a non-square system of equations? Okay, well, a non-square system of equations is a system of equations in which the number of equations differs from the number of variables. So for example, if I have 3 variables and yet only 2 equations, that's a non-square system of equations. And we're not going to worry about an equation in 3 variables. We're not worrying about partial fraction or partial fraction decomposition today, okay? So let's just start talking about row echelon form and back substitution. We've talked about back substitution before, but when elimination is used to solve a system of linear equations, the goal is to, and this is for row echelon form, the goal is to rewrite the system in a form where back substitution can be used. So do you remember what back substitution is? It's when you kind of work backwards, where instead of starting and solving down, you start at the bottom and you solve backwards. So like this one, this example, which is in row echelon form, we're going to use back substitution. to solve these variables. What's cool about this, do you see how it's in that stair-step pattern that makes it row echelon form? And we have a solution, z equals 1. So when we back substitute, we're going to substitute this backwards, meaning going upwards instead of forwards. So we're going to say, okay, well, if y minus 2 times z, which is 1, equals 4, then y minus 2 equals 4. Add the 2 to both sides, we get y equals 6, okay? And then now we're going to substitute it back again by plugging it backwards into this z and into this y. So we end up with x plus y, which is 6, minus z, which is 1, equals 9. And we're going to solve for x. X plus 6 minus 1 is just plus 5. Subtract both sides by 5, we get x equals 4. And now remember, and when we write this solution, we always go x comma y comma z in alphabetical order. So this is going to be 4 comma 6 comma 1. And we're done with that. So let's talk about Gaussian elimination a little bit more. To solve a system that's not in row echelon form, first, you're going to convert it to an equivalent, so meaning we're not doing anything that's not equal, system in row echelon form using one or more, usually more, elementary row operations. And you're probably thinking, Mrs. Stiles, you talked about this before. What does that mean? What are elementary row operations? Here they are. List the 3 row elementary operations that can be used in a system of linear equations to produce an equivalent system. So the first one is that you can interchange 2 equations. So the reason why this is helpful is because we want to get it in that stair-step pattern. So sometimes if one row has less variables than the other, we want to switch those, the order of it, and we can interchange them. Another one of the elementary row operations is that we can multiply one equation by a non-zero constant. So we can multiply things by a coefficient other than 0. And then lastly, our last elementary row operation that we can do is that you can add multiple of one equation to another equation. Okay. And I know this doesn't make a lot of sense right now, but it will in just a second. So make sure that you keep that list really close to you because we're going to be using it. Okay. And then we're talking now about the number of solutions a system of linear equations in more than 2 variables. It has to fall into these 3 categories. Either it has exactly one solution, it could have infinitely many solutions, or it can have no solutions. Okay, so here's the deal. In order to solve the system of linear equations, we need to get this into what we were doing before. We need to get this as a row echelon form, which we saw that before in example number 1. Do you see how, remember how easy that one was to solve with 3 system equations? So we're going to do the same thing, but we're going to use our row operations to get the system of equations in row echelon form. But here's what I want you to do. We're going to run out of room if I try to do it right here. I want you to go either on, if you printed this on one side, either go on to the back side of the page before it or on another piece. Okay, so now that you've got your your either separate piece of paper or your back sheet of paper. Now we're going to start on that example number 2 where we're going to use the elementary row operations to get this into row echelon form. So again, our goal is to make it look like row echelon form. Okay, which remember, row echelon form looks like something like x plus y plus z. So, 3 variables in the top equation, something y and something z in the second equation, and just z in the third, okay? This is not what exactly it should look like, but the top should have 3 equations, the middle should have 2 equations, and the bottom should have 1 variable. And when I said equations, I meant variables. So 1, 2, 3 variables, 1, 2 variables, 1 variable. And again, our list of things that we can and cannot do is we can interchange equations. We can multiply an equation by a constant not equal to 1. And we can add multiples of an equation to another equation. So these are the 3 choices we have. Okay, so here we go. So this we'll call the equation in row 1. This will be the equation in row 2, and this is the equation in row 3. So when I'm looking at this, I see here, I want to keep row 1 the way it is pretty much. I want there to be 3 separate variables here, which it has. So my goal in this first is that we're going to fix row 2, which means that we need to eliminate the x in row 2. So let's figure out, okay, if I know that there's this 2x in row 2, I need to figure out a way to eliminate it. So what I am seeing is I could take and multiply a -2 to this x, add it to this one, and that would eliminate the x in that row. So that's what we're going to do. Okay, so here's what we're going to do. We're going to take -2 and multiply it by the row 2 equation. And we're going to add it, excuse me, not row 2, pardon me, row 1 equation. Because remember, we wanted to turn x into a -2x. And we're going to add it to the row 2 equation. When we list what we're doing, the last row equation that we're talking about is the one that we're replacing it with. So the way we start this is first, we rewrite the rows that we are not changing. So we're not changing row 1 and we're not changing row 3. So we're literally going to rewrite it. Here's row 1 and here's row 3. Now I am going to do the change in row 2. So here we go. We're going to take that -2 times row 1. So what's -2 times x plus this 2x? Well, -2x plus 2x is 0. -2 times y is -2y plus -y. So -2y plus -y gives me -3y. And then -2 times z is -2z plus 3z is just z. -2 times 3 is 6 plus 16 is 10. Okay, so that's my first step. I just eliminated the x for my row 2, which is beautiful. I put a 0 there so you could see it, but it doesn't really need to be there. So beautiful. We've got our row 2 eliminated. Now what we're going to do next, because our row 2 is now exactly the way we want it, our next step is we're going to eliminate x in row 3. So in order to eliminate this x in row 3, what are we going to have to do? Well, I know, let's see, in order to eliminate x, I could multiply row 3 by a negative right here. So if I made this a negative, this negative x, and I added it to row 1, that would eliminate those x's. So that's what I'm going to go ahead and do. I'm going to say I'm going to take row 1 and add it to a negative 1, or a negative times row 3. And again, whatever the last row is mentioned is where we're doing that step. So again, we're going to rewrite the rows we're not changing. So we're not changing row 1. We're just writing that down. We're not changing row 2 the way we left it. So now we're going to do that change to row 3. So here we go. Row 1, which is x, plus a negative row 3, which is negative x. So that's going to give me a 0x. And now we've got row 1 plus a negative row 3. So a negative negative 2 is a positive 2. So we've got 1y plus 2y gives me 3y. And then z plus a negative z, that's going to give me 2z. And then 3 plus a negative 1 is 2. Okay, so what I've got now is I've eliminated the x in row 3. And now in order to make it look like that row echelon form, now we're going to eliminate y in row 3. So my next step is going to say, well, in order to eliminate y, one of the things I could easily do is add row 2 to row 3, and that would eliminate these y's. So that's what I'm going to do. I'm going to say row 2 plus row 3. And again, the last row mentioned is where the row change is happening. So I'm going to keep everything else the same, rewrite them. Here's row 1. Here's row 2. And now for the change. So row 2 plus row 1 for the y's just gives me 0y. Row 2 plus row 3 for the z's gives me 3z. Row 2 plus row 3 gives me 12, which is beautiful because I've just eliminated that y in row 3. So we're almost to row echelon form. And I don't know why there's a black spot underneath here, but that's okay. We're almost to row echelon form. The only difference now is in order for this to be row echelon form, this needs to not say 3z, it needs to say z equals some number. So I'm just going to take row 3 and multiply it by 1/3 because that will take away the 3. So again, I'm going to rewrite row 1, row 2, and let's see if this will let me write on top of it. And then row 3 is going to be 1/3 of 3z is just z, so it's not going to let me write on top of it. So I'm going to have to bring this up over here. Row 1, row 2, and then here's row 3, which is 1/3 of whatever row 3 is. 1/3 of 3z is z, 1/3 of 12 is 4. So now this is in row echelon form, and now we can solve it. So here we go. If z equals 4, we plug it back in to the z right here, and we end up with negative 3y plus 4 equals 10, which tells me that negative 3y equals 6, which gives me y equals negative 2. Once I have that, I can plug z into here and y into here. We end up with x plus negative 2 plus z, which is 4, equals 3. So we get x plus 2 equals 3. So if I subtract it, I get x equals 1. And my solution is x, y, z. Okay? And then finally, we talked about consistent system, which means it has one or more solutions, but when it has exactly one solution, this is called independent. So remember, it looks like this. When it has exactly one solution, we've got 1, 2 linear equations, and there's only one solution. A consistent system with infinitely many solutions, we call that dependent. And we call it dependent because in that case, it's 2 lines that literally are exactly the same, like that. So that's what we call a dependent system. Okay, we're not doing example 3 or the rest of that last page, so you can skip all of that, and I will see you back.